Okay, let's unpack this. Have you ever tried feeding like a really, really long video to an AI model? And then your computer just, I don't know, gives up, throws its hands in the air.
Oh, yeah, that feeling.
It's not just your machine being dramatic, though. It's actually a huge challenge for these powerful transformer-based large language models, LLMs,
Hmm.
they're the backbone of most multimodal AI now, but they seriously struggle with long videos. And the main culprit is this thing called quadratic scaling. It hits memory, it hits
It's
computation,
hard.
right? And it's not just some like minor technical glitch. It's a real barrier. It makes
Uh,
understanding rich, detailed, long videos pretty much impossible with the usual
I
methods.
don't think you understand, though.
Yeah.
You try watching, say, an hour-long video with your fancy transformer LLM.
Mm-hmm.
Okay, maybe it gets 10 frames in, maybe. And suddenly your GPU memory just screams and it
Yeah.
just crashes.
Yeah.
And you realize, oh, right, quadratic scaling. Every single new frame has to pay attention to all the previous frames.
Every single one.
So you think, well, what if we just didn't? What if we brought back the RNN? That old friend, remember those? Constant size hidden states. Suddenly, you can handle maybe 10,000 frames on a regular 24 gig GPU. Silence.
Okay.
But then someone pipes up, yeah, but RNNs forget things. Their context is too short. Fair point.
Mm.
So you add something called sorted visual token merge, which is basically a fancy way of saying you intelligently sort of squish the redundant visual info together.
Squish it. I like that.
And you even sort them by size, ascending order,
Get
because it works. Science. And it actually works even for videos way longer than anything it was trained on.
Wow.
And someone else says, but it's only like 2 billion parameters, and you just point to AuroraLong and how it's outperforming models 38 times its size on long video Q&A.
38 times.
Then they say, but you only use public data. And you show them it beats proprietary big guns like Gemini 1.5 Pro on dense captioning. But it's not real video understanding. And your model is sitting there processing 12-minute videos, generalizing from training on less than 60 frames.
Okay, point made.
They go quiet. And you realize you didn't just build another video model. You built a bridge. A bridge between this flood of long-form video data and efficient, smart understanding, making it accessible for everyone. So yeah, our mission today is to really deep dive into AuroraLong. It's this super efficient model, and it's genuinely bringing RNNs back into the spotlight for understanding video.
Okay, great. So what does this all mean for you, our listeners, interested in the cutting edge of AI? We're going to explore AuroraLong's core innovations, how it actually works under the hood, and frankly, why it's such a big deal for AI's ability to, well, watch and understand video. All right, so here's where it gets really interesting. Let's talk about the specific problems, the pain points that AuroraLong is really designed to fix. Why exactly do long videos cause such problems for current models? This quadratic scaling thing, what's the deal?
Right. The fundamental challenge, it really boils down to just one kind of brutal fact. Current large multimodal models, the LLMs, they're usually based on transformer architectures, right? Like LLaVA. And they just get exponentially hungrier for memory and processing power the longer the video gets.
Exponentially.
Now, quadratically, it's not just a bit more, it's the square more.
Yeah.
That's the infamous quadratic scaling.
Yeah.
It makes processing something like a full movie just practically impossible, or at least incredibly expensive.
Okay.
See, with a transformer,
Yeah.
every new frame of video basically has to chat with every single previous frame to figure out the context. This all-to-all attention. It's brilliant for short stuff, language, short clips.
Sure.
But the cost, computation, and memory, it just explodes quadratically as the video gets longer.
It's like managing a conversation where every new person has to individually talk to everyone who's ever been in the chat before.
Exactly. It quickly becomes totally unmanageable. And, while the part that looks at the image, the visual encoder, like a VIT, that scales okay, linearly mostly. It's the LLM part, the language model. That's the real bottleneck for long sequences.
Got it. So it's the language understanding part trying to connect everything over time that hits the wall.
Precisely. It's a fundamental barrier.
Okay, so transformers are hitting this wall. Quadratic scaling. Clear limitation. So what's AuroraLong's big idea, and why are we suddenly talking about RNNs, recurrent neural networks, again? I thought they were kind of old news. Superseded by transformers.
Yeah, that's a great point, and you're right. For a long time, transformers definitely ruled the roost. But AuroraLong brings RNNs back, but with a really crucial modern twist. The core idea is swapping out that transformer-based LLM component in the multimodal model
Right.
with a linear RNN language model. Specifically, they use something called RWKV, stands for Receptance Weighted Key Value.
RWKV.
It's a newer type of RNN, kind of a hybrid, actually. Now, the key advantage, the classic advantage of RNNs for sequential stuff like video, is they use constant size hidden states when they're running during inference.
Constant size.
Meaning the memory needed for processing doesn't really grow much even as the sequence gets longer and longer.
Ah, okay. Unlike the quadratic growth with transformers.
Exactly. So using your analogy, instead of the new person in the chat needing to remember every single past message from everyone,
Yeah.
the RNN just keeps this small, involving summary of the whole conversation so far. It just constantly updates it. Way more efficient.
Like keeping running notes instead of a full transcript.
Kind of, yeah. And what's really neat about RWKV, this specific RNN, is that it manages to combine the training efficiency of transformers. You can train it in parallel, which was a big drawback of old RNNs.
Right, they were slow to train.
With the efficient sequential inference, the constant memory cost of RNNs, it's really trying to get the best of both worlds. It addresses those old training issues, but keeps the memory benefit.
Wow, that's genuinely clever. It's like rediscovering a classic technique but giving it a serious upgrade. So they looked at the problem and said, let's bring back the old school but make it work for today.
Pretty much.
Could you walk us through the architecture choices then? How did they actually build this thing?
Sure. So for the vision encoder, the part that sees the frames, they used a pretty standard but powerful model called SIGLIP. And what's important here is that the bottleneck wasn't really the vision part itself. Vision transformers already scale okay linearly. The memory hog was the language model.
Okay, so SIGLIP handles the seeing part efficiently enough.
Right. Then, to connect those visual features from SIGLIP to the RWKV language model, they use something pretty simple. Just a two-layer MLP, a multi-layer perceptron. That's the bridge.
A simple connector.
Yeah, nothing too fancy there. But then there's this clever sandwich prompting strategy.
Sandwich prompting sounds tasty.
Maybe. It means they take these merged visual tokens we'll talk about, reorder them, and then place them between the instruction tokens they give the model.
Ah, so instruction, then visual info, then maybe more instruction.
Kind of like that, yeah. And this is actually pretty crucial for RNNs like RWKV. They don't have those explicit context extension tricks that some transformers use. So this careful prompting, the sandwiching, helps the RNN follow the instructions better and process the mix of visual and text info effectively.
Okay, that makes sense. You have to guide the RNN a bit more carefully with the input structure. So we've got this efficient RNN backbone solving the scaling problem. Great. But long videos still mean just a ton of visual information, frame after frame, right?
How does AuroraLong handle that flood of data without just overwhelming the model anyway, or hitting the context limits of even the RWKV? That seems like another hurdle.
You're spot on. That's the other key piece of the puzzle. It's called Sorted Visual Token Merge, or STOME.
STOME. And it's a really crucial complementary strategy. Its main job is to drastically cut down the sheer number of visual tokens coming from the long video. This is super important because, like you said, even though RWKV is efficient in how it processes a sequence, its pre-trained context length is still limited about 4,096 tokens in this case.
All right.
And raw video, that can easily spit out hundreds of thousands of visual tokens. STOME basically narrows that huge gap between the massive visual input and what RWKV can comfortably handle.
So it compresses the visual information before it hits the RNN.
Exactly. And the way it does it is quite smart. And importantly, it doesn't require extra training. It's training free. First, it merges similar visual tokens spatially within each frame. So looking for redundant patches inside one picture.
Spatially, not temporally across frames.
Right. They found that frame-to-frame similarity, especially at typical video rates like 1 frame per second, often isn't that high anyway. So spatial merging within the frame was more effective. But here's the really unique part, how they reorder these merged tokens. After merging, they sort them based on the number of original visual patches they represent.
Okay, so tokens representing bigger original areas get sorted differently.
Yep. And here's the kicker, the really crucial finding from their experiments. Sorting them in ascending order works best.
Ascending, so tokens representing fewer original patches come first. That seems backwards.
It does seem counterintuitive, doesn't it?
Yeah.
You'd think the most important bits, the bigger chunks, should go first. But the theory is this actually helps RWKV's specific way of processing information. It's called data-dependent token shifting, basically how it prioritizes things it sees. Putting the smaller chunks first helps it better use its pre-trained ability to model text sequentially and helps it memorize the critical info, especially from the larger patches that then appear later in the sequence.
Huh. That's fascinating. So the order matters a lot for how the specific RNN learns and remembers.
It seems so. And for you, the listener, this clever compression, this S-tome, is really key. It lets the system feed way more video data into the efficient RNN without losing the important stuff or hitting those context limits. It's what makes long video analysis actually practical on more normal hardware.
That's a really interesting insight. Sometimes less is more, or at least ordering it differently is more effective, which brings up the question, how do you actually train something like this? It sounds like a pretty delicate balancing act, right? Teaching different parts, vision, language, then getting them to work together for video in this specific RNN way.
It definitely is a deliberate process. They laid out a clear three-stage training strategy. And something really significant here is that all the data they used is publicly available.
Oh, that's great.
Yeah, it really lowers the barrier for other researchers to reproduce their work, build on it. It's a big step for, democratizing this kind of AI research.
Okay, so what are the stages?
All right, stage one is pre-training. The goal here is basically to teach the model how to align the visual features from that SIGLIB encoder with the word embedding space of the RWKV language model, how vision translates to language concepts. In this stage, only the connector, that simple two-layer MLP, is actually trained. The big vision model, VIT, and the LLM itself are kept frozen.
Okay, just training the bridge first.
Exactly, using mostly image caption pairs, just getting that basic visual language connection established. Then comes stage two, the vision stage. Here the goal is better vision generalization, make the model better at seeing diverse things. So now the vision transformer, the SIGLIB part, is unfrozen and trained. But the LLM, the RWKG part, stays frozen.
Why freeze the LLM now?
Good question. They do that to avoid hurting its language abilities. Image datasets often have short or maybe not so great labels, and you don't want that to mess up the LLM's pre-trained language skills.
Protecting the language core while boosting the vision. Makes sense.
Precisely. They use various image-based computer vision datasets here to make the vision part more robust. And then finally, stage three. The language stage. This is where everything comes together. End-to-end training. High-quality public data. Now, both the VIT and the LLM are unfrozen. They learn together.
The whole system learns.
The whole system. They use both single-image stuff and multi-image, video samples. And they use that low visual token retention ratio, like 0.1 we talked about with this tome, for efficiency. Lets them cram more frames into training. They start with single-image data, then transition to video data sets, often using a lower learning rate, really focusing on things like video captioning and question answering.
So it's a very careful step-by-step process, like teaching different skills sequentially before combining them for the really complex tasks.
Exactly. Very deliberate.
Okay, the crucial part then, does it actually work? Let's get to the bottom line, the results. Performance, efficiency. Does it deliver?
Yeah, and the results are frankly pretty compelling. They really hit the core problem head on. First, let's talk efficiency. This is huge. AuroraLong's GPU memory cost. It's approximately constant, or it only grows linearly with the number of frames.
Not quadratically.
Not quadratically. That's the win. They measure it as having a 34x memory advantage over a comparable transformer model, like Intern VL 1.52b, when you're processing, say, 1,024 frames. And the headline number, it can handle over 10,000 frames on a 24 GB GPU.
10,000 frames on a consumer-ish GPU. That's...
Wow. It's a massive difference. And inference speed, getting answers out. They saw an 8x improvement for 1-minute-long videos at 1 frame per second compared to baseline transformer models.
Yeah.
Faster and way less memory hungry.
Okay, efficiency is clearly a home run. What about the quality? Does it understand the video well?
Right, performance. So even on short video understanding, AuroraLong, despite being relatively small at 2 billion parameters, actually exceeds Gemini 1.5 Pro on average in VDC. That's a benchmark for dense captioning, describing lots of things in short videos.
Better than Gemini 1.5 Pro on that. Impressive.
Yeah, and it generally outperforms existing open models with much larger parameter counts on various short video tasks. But where it really shines, as intended, is long video understanding. It shows really impressive zero-shot long video understanding, meaning understanding long videos without specific training on those long formats.
Zero shot, okay.
It gets competitive or even superior performance compared to much, much larger transformer models, some up to 38 times its size. And also against other open state-of-the-art models on benchmarks like MLVU and MovieChat 1K. And these benchmarks aren't trivial. They feature videos with an average length of around 12 minutes.
12 minutes average,
Yeah.
and it's keeping up with models 38 times bigger.
Exactly. And what's perhaps most remarkable is the generalizability. Remember, its RWKV brain was pre-trained on text sequences of only 4,096 tokens long.
Right, pretty short context.
And AuroraLong itself was only trained on videos less than 60 frames long. It's like 2 seconds of video at 30 Ferris.
60 frames, that's it.
That's what they report for the main video training stage. Yet, it generalizes effectively to understand these 12-minute-long videos it's never seen before.
That's incredible generalization. It really learned the underlying principles, not just memorizing short patterns.
It strongly suggests that, yeah, it learned to handle sequences in a fundamentally efficient way.
It's like it learned to run doing short sprints, but somehow figured out marathon running without extra training, and it's cheaper to run. That's massive for innovation.
Absolutely. It lowers the barriers significantly.
Did they find anything else surprising when they took it apart? Those ablation studies you mentioned? Anything beyond the ascending token order?
Yeah, a couple of interesting things came out. That token merging ratio we talked about. S-home compressing the tokens. Yeah. They found, kind of counterintuitively again, that for some video captioning tasks, performance actually seemed to get better at lower token retention levels, like keeping only 10% 0.1 ratio.
Better with less visual information kept? How does that work?
It's puzzling, right? Their hypothesis is that the RWKV model's recurrent state, its internal memory, might actually be over-parameterized for the relatively short visual context it sees per frame during training. So giving it highly compressed information might actually force it to distill the meaning more effectively, playing to the strengths of its recurrent nature. It's a weird quirk, but suggests these RNNs might thrive on condensed input sometimes.
Fascinating. Almost like it focuses better when it's not overwhelmed.
Possibly. And the other thing was just confirming that input token order really mattered. Sorting those merged tokens in ascending order by the number of original patches. That empirically gave the best results, validating their theory about helping the RWKV memorize and model sequentially.
So the quirks seem to lead to real benefits. What's next then? What are the current limits or the next frontiers for AuroraLong? Is it ready for everything, or are there still challenges?
Oh, definitely still challenges. It's presented as a prototype, a strong baseline. The authors are upfront about limitations. One they mentioned is limited multiple-choice question answering performance. They think this might be due to the relatively small size of the pre-trained RWKV model they used. Bigger base model might help there.
Okay, so complex reasoning might still be tricky.
Possibly, yeah. And they also mention challenges in specific domains, which basically means while it's great academically and broadly competitive, it might need more specialized training or fine-tuning for certain specific real-world tasks, like medical video analysis or something very niche.
Makes sense. General models often need specialization.
Exactly. So the main path forward they point to is using higher quality training data. Better data, more diverse data, could help push performance further and address those specific weaknesses. They really position AuroraLong as a strong baseline for these kinds of hybrid architectures, mixing RNN ideas back in. They're hoping it encourages more research into non-transformer LMMs for long video.
So it's a proof of concept and a call to action for more diverse architectures.
I think that's a great way to put it.
Okay, so just to recap for everyone, AuroraLong is this really clever mix, right? Bringing back efficient linear RNNs, combining them with this innovative sorted visual token merge strategy. And the result is pretty unprecedented long video understanding, but on much more modest, accessible hardware. It's a potential game changer for efficiency and just access in this field.
Absolutely. And if you think about the bigger picture, this isn't just, making AI slightly better at watching YouTube. It's really about democratizing access to these powerful AI capabilities.
How so?
Well, by making long video understanding so much more efficient, runnable on less powerful machines, AuroraLong opens the door for tons of applications that were just too expensive or computationally impossible before. Think about students in areas with limited resources getting AI summaries or analysis of long educational videos, or scientists analyzing hours and hours of, say, wildlife camera footage or biological recordings without needing giant cloud computing budgets.
Yeah, it shifts the power away from just those with massive data centers.
Exactly. It could be sophisticated AI analysis to more common hardware, to more people, more researchers, more creators.
So final thought for you, the listener. What really stands out to you about a model that can grasp a full movie almost as easily as a tiny clip, and does it using just a fraction of the compute power we thought was necessary? Imagine the new kinds of stories that could be told, the insights hiding in all that long-form video data that we could finally unlock. When deep video analysis becomes truly widespread, truly accessible, what could you build or create or discover with that kind of capability in your hands?